So thank you all for being here today at the seminar. It's a pleasure to have Pratik Chaudhari. He is in Ukraine and he works on many different things. As he was telling me before, apart from deep learning and small data, which is another very interesting area that he's working on. He's also working on robotics, which is what he's training most is on. Am I right?
Close, yes.
So today he will be talking about deep learning and in particular data data and use capacity control in deep learning. Okay. So thank you very much for coming. And
yeah, so thank you for inviting. Thank you for coming here. I spent a lot of time in Boston, but I've never been inside the BU campus. There are all these bars on Brighton. That is where I've mostly been. I want to tell you today about two papers that we have recently. It's a long story of trying to understand why neural networks work well. We know that they do. So it's a little bit moot to say why they work well. Everyone can use them. We know they work well. This is some kind of building an understanding of why is it that they work well for typical kind of problems. If we see them break, how can we go around fixing it? This is the goal of the kind of theory that I would like to build personally. I would contend that there are two key questions that we do not understand very clearly. There are many others. These are the two that I have spent some time looking at. The first one is why is it that we can train neural networks efficiently? We know that they are very large objects, millions of weights. The data sets that we use are also very large. The function is not clearly convex. So by all measures, this is a very, very hard problem to optimize. And yet you and I can train a network pretty well, even on a laptop these days. So something clearly must be easy about the problem that we are solving. Otherwise, we wouldn't be able to do it. So what is it that is easy? And spent a lot of time during my PhD trying to say that the loss function of neural networks is relatively benign. It is not convex, but it is not horrendously non-convex. And that is why we can, typical algorithms like SGD work well. So this is one way to understand this question. The second one, which I'll talk more today, is about understanding why the networks do not seem to overfit. In high school, someone told you that if I give you 10 data points, you should not fit a polynomial of degree 20 to these 10 data points, as obviously that looks like a bad idea when you see the polynomial doing funny things. In deep learning, we love to do this. We fit huge models on relatively small amounts of data, even if the data is actually large, but the model is even larger. And not only do we not get hurt by this, we also improve things if we fit an even larger model. So the same amount of data, 50,000 samples, 100,000 samples, you fit millions and millions of weights. And if you fit even more, you still end up doing better. So this clearly doesn't make any sense. It goes against what just polynomial regression will tell you. So that is what we would like to understand. What is it in the problem that allows you to overfit without getting hurt? Okay. I want to begin I want to motivate these questions with a few peculiar findings that we see in deep learning. The first one is an old paper of mine where we found that if we take a trained neural network and we calculate the Hessian of this trained neural network, the Hessian measures the curvature of the loss function. So the directions in which the eigenvalues that are large, the eigenvectors corresponding to those eigenvalues are directions in which I can perturb the weights and my loss changes very quickly. And vice versa for the small eigenvalues, I can perturb the weights along those eigenvectors and my loss is relatively unchanged. So after training typical neural networks, we found that a very large proportion of the eigenvalues is essentially zero. So in this network, about 95% of the eigenvalues are very close to zero or near or zero up to numerical precision. And of course, there are a few eigenvalues that are positive. These are kind of the walls of your energy landscape in which you shouldn't climb up. And there are also a few negative eigenvalues, which tells you that this is not really a local minimum that you have found after training. It is a saddle point. There are both directions along which the loss decreases. There are few of them. And there are lots of directions that are near zero or increasing. Now, such regions are, you can do some kind of calculations in statistical physics to convince yourself that such regions are not normal. For many problems, such regions are rare in the energy landscape. You have a huge function, you have a very high dimensional space in which you have a loss function. There are many regions in this loss function which work well for your training data set. Most of them do not look like this under certain calculations. Okay, so first of all, it was kind of a little surprising to see that typical training methods for neural networks find regions like this. They are very hard to find. It's like taking this large room and then finding like one little dot in this room with this particular geometric property, whereas there are many other solutions that do not have this large proportion of zero eigenvalues. Okay. That said, we know that when algorithms typically end up in regions that do not have such a large fraction of zero eigenvalues, they do not generalize well. This is what we had noticed a few years ago. And so we said, okay, we know that SGD-like methods end up in these wide regions. We know that SGD-like methods also get good generalization performance. So why don't we change the loss function in a way that artificially biases the method towards such wide regions to begin with? That way, all the regions that do not look like this, that are sharp, roughly speaking, they will not even exist under this loss function. So there is nothing else to do but find the good regions. And so we were using objectives of this kind. It basically takes the original objective, f of w, which is your original loss function, the average of the error on all your samples, and it convolves it with a Gaussian kernel. So this convolution basically smooths out stuff in the local neighborhood, and it kills all the regions that change very quickly, the sharp regions, and it preserves the regions that are wide and do not change much. Okay, and so we had a reasonable amount of success training neural networks with these kinds of objectives. You can also show that they get good generalization error. So you can create algorithms out of such way of thinking. But as I said, such regions are peculiar. It's peculiar why SGD ends up in such kind of regions. The second peculiarity of stochastic gradient descent is as follows. So we know that the objective is not a convex function. So for non-convex functions, if you start at two different initial conditions, you will end up at two different locations, right? And there is nothing to say a priori which one of the locations you will end up at, given your initialization. You can think about this problem in a slightly different way and say that I'm not interested in understanding one trajectory of SGD. I'm interested in understanding what happens if I keep running SGD for an infinite amount of time. We know that SGD is a stochastic process. So long as the process is ergodic. Ergodic simply means that it reaches all parts of the parameter space infinitely often. So long as this process is ergodic, it will end up at all parts of the space. And now I can ask myself, what is the likelihood that it ends up in good regions versus what is the likelihood that it ends up in bad regions? This is a kind of a little pointless exercise in the sense that you will never train a neural network for an infinite long amount of time. But it may tell you something about what are the typical locations that you can find neural networks at after training them. So you can either take one network and train it for infinite time, or you can take an infinite large number of networks and train it for finite number of time. If things are ergodic, you should see similar results in your observations. Okay. So we had done this kind of analysis where we said, let us not worry about one trajectory of SGD. Let us think of the outcome of SGD as a probability distribution on the weight space. This is a probability distribution of weight space. It begins at whatever location you initialize at, a Dirac delta, and under steps of SGD, it goes wherever it goes. And typically you can, this is a very easy exercise. You can also show that there is only one location that it can go to, okay? It has to have large probability mass in regions where the training loss is small. It has to have small probability mass in regions where the loss is large. This is the solution. You can write it down as what is called a Gibbs distribution. E to the negative f is the solution of such problem. Well, all this is true if the noise in SGD lets it move in many different directions with equal mobility. What happens for typical data sets and typical neural networks is that the noise in SGD does not let it move in all directions. So you might have seen stuff like detailed balance in your class on Markov chains. Detailed balance simply says that a trajectory run forwards in time is equally likely as a trajectory run backwards in time. So if you go away from one location, you have an equal probability of coming back. But this doesn't hold because of the special kind of noise that you have in SGD. The noise is not isotropic. And for such systems, you can get somewhat pathological phenomena where the solution that SGD ends up at in this slightly more abstract case is not e to the negative f. It is some other functional, and you can connect it to ideas in optimal transport, etc. But all the moral of the story is that the noise of SGD in deep learning is not isotropic, and that causes a fundamental difference in the kind of solutions that you may end up at. Stuff that is likely under situations where the noise is isotropic is not necessarily likely under this setting, and vice versa. Okay, so these are two particular peculiarities. There are many others that people have found over the years. But okay, so as I said, we can also use these objectives that bias the training towards flat regions to get very good performance. So this is still, I would contend, some of the fastest methods to train neural networks. So the black line is the validation error of a residual network on CIFAR. And this is a good network, so roughly 4% error or so. And this is 2017, so it is even better. But with these algorithms that we have cooked up, even after the first epoch, even if the first epoch is quite, the algorithm is much slower than SGD in terms of the number of iterations, but even after the first epoch, you're already sitting at a solution that is much better than what you get in SGD. So these are good algorithms for training neural networks, some of the fastest ones I know. Okay. Today, I would like to convince you that in our quest for understanding deep learning, we are missing one very fundamental point. So if you ask people, they will say that, oh, SGD works because of architectures. This was the case in 2015 when people found that convolutional networks work really well. Everyone was very happy because voila, like computer vision people have always believed in convolutions. And then they said, look, we have finally found that they are so much better. Well, in 2020, transformers also work well. So clearly, if convolutions were so special, then transformers are also special. Or the alternative is that none of them are special. So there is clearly like an inductive bias that we create from the architecture, but it's not as if only specific kinds of architectures work. Most of them do work. Okay. Some other people will say, oh, look, like these models are all over-parameterized, and that is the real secret of why deep learning works. You can take a small neural network, train it on your laptop, it will work much better than other machine learning models. So small networks also work. It's not as if you need large networks. Large networks do work better, but small networks also work. And in a more fundamental sense, over-parameterization gives you a lot of redundant dimensions in how you make predictions. By definition, the redundant dimensions are redundant. They should not be affecting how you make predictions. They may make it easy to find these functions, but really like the function that you're fitting is not a high dimensional function. So if over-parameterization is the secret sauce of deep learning, then that is not a complete way of understanding it to begin with. And I can go around and like point out many such incongruences in how we try to understand deep learning and where we hit a wall. But I want to convince you that the elephant in the room that we are missing is really properties of the data. If we do not model explicitly the properties of the inputs and the outputs that we use in machine learning, then it's a little unsatisfying to build a theory on the models that we fit to this data. And I will show you or convince you that a lot of the properties that we see as peculiarities, or a lot of the properties that we think we do not understand, are really just coming from the inputs. The networks have very little to do with it. Okay. So I'll talk about this paper. This paper was led by two students in my group, Rubing Yang, who is in her third year in the applied math program, fourth year, I think. Jialin Mao, who is in her fifth year in the applied math program. So this was presented at ICML a couple of months ago. You'll also find it on our talk. Okay. Let's begin with an experiment. I like to do this. So focus on the blue line. The blue line are the eigenvalues of X transpose. X is a matrix. Every column of this matrix is one image of CIFAR 10. So one image of CIFAR 10 has 3072 dimensions. So every column has 3072 rows. And there are 50,000 columns for the 50,000 training samples. So X transpose measures the correlations of the different pixels in your CIFAR 10 images. And the blue lines are the eigenvalues of this correlation matrix. We believe that input images lie on low dimension manifolds. For 50 years, people have been studying this. They don't quite lie on an exactly low dimension manifold. They lie on an effectively low dimension manifold. Stuff falls quickly after about 100 dimensions. That is really where most of the data lies. And then there is a long tail of dimensions in which there is weaker and weaker variation in the data. Okay. So if you want to think about this more intuitively, blue sky lies on the right end of the spectrum in the tail because there is not too much variation in the blue sky. A blue dog also lies in the right tail of the spectrum because there is only 3 blue dogs of the 3 people who colored them blue, right? The most interesting stuff happens in the head of the spectrum, okay? This is just about the inputs, nothing to do with the networks yet. What we can show, and this is an experiment that suggested this calculation, is that when you train a neural network on such kinds of inputs, the neural network essentially mirrors this structure. So the orange line is the Fisher information matrix of a trained neural network. So there is lots of nuances and tricks of how to calculate these very large objects. The Fisher information matrix is a matrix, so size is the number of weights times the number of weights. So there's a lot of grief that goes into calculating it, but you can. It measures the curvature in the output space. How quickly do the outputs change if I perturb my weights? Just like the Hessian measures how quickly the loss changes. The loss is an average over all the samples. Fisher information measures actually the output itself. If you have 10 classes, the output, it will measure the curvature of this 10-dimensional space. Okay. The eigenvalues of the Fisher information matrix follow essentially the eigenspectrum of the input. And this is a very important thing to understand because for linear regression, if you write down y equal to x transpose w, the Fisher information matrix and the Hessian for linear regression is exactly x transpose. So the orange line and the blue line are identical for linear regression. And what I'm showing you is that for the neural network, they are pretty damn close also for the trained network. Okay. Now, we call such matrices sloppy. We call them sloppy for the following reason. So think of one eigenvector in this tail. It corresponds to a combination of weights, and I can perturb those weights by huge orders of magnitude before it starts affecting my output. Here, I can perturb it by a good 6-7 orders of magnitude up to float precision, essentially, without ever changing my output. So if you see a blue dog in the tail, and you overfit to the blue dog, you call it a dog because it is blue, or you call the sky blue because it is a dog, you don't get hurt by it very much because there is very, very few samples like this. The tail is very small or has a much lower power than the largest eigenvalues. And that is why you can happily overfit the tail without seeing the hurt, okay? The head of the spectrum is all the dominant ways in which you are making predictions. And what this plot is also suggesting is that the function that is learned by the network is effectively a low dimensional function. For the orange line is a network with, I think, about 1.5 million weights. And roughly speaking, about 1,000 dimensions of this function are good enough to make predictions on this data set, okay? What we can show is that essentially any quantity that you can care to calculate inside the neural network has this kind of a shape. Stuff falls quickly in the beginning and then decays with so-and-so slope in the tail. Okay. So like I said, the head of the eigenspectrum corresponds to the purest kind of sample. So this is a picture that I pulled for like a Plato's theory of forms. So the most canonical cat and the Platonic cat lies in the head. And then like the weird stuff lies in the tail, or the most boring stuff lies in the tail. Okay. So the structure of the Hessian, the Fisher information matrix, the eigenvalues of correlations of the Jacobians, of the logits, correlations of activations, correlations of gradients of activations, everything that you can care to calculate has shape like this, which is very surprising a priori if you did not know this. People have seen effects of such results many, many times in many literature. So manifold learning for neural networks works nicely because the manifold is low dimensional. You can prune the networks because the networks are low dimensional to begin with. Well, pruning typically is done by reducing some of the weights to zero. What this picture is says that you should not reduce some of the weights to zero, you should reduce combinations of weights to zero, right? So you are projecting in not the bare parameters, as I like to say, the weights, but along some eigenvectors. So we are seeing and exploiting the effects of such stuff day in and day out. But it is a little shocking how dramatic this, how dramatically low dimensional the structure is. Okay, so more precisely, what you can show, and this is not a very difficult calculation, is that the trace of the Fisher or the trace of the Hessian are upper bounded by, I think there should be a trace sitting here in front of the blue stuff. The trace of the input correlations, which is exactly the eigenvalues that we are plotting, times some function of the weights. So it is true, this bound holds for any weights. We have plotted that particular picture for the trained weights. Okay. One way to understand this inequality is that if I take the network and make it much, much, much bigger, as the number of weights increases, the dimensionality of the Fisher increases, the number of eigenvalues in the Fisher increases. But if this right-hand side is fixed, let us say by doing weight decay or projecting it on some ball of weight space, etc., the blue stuff is fixed. So the right-hand side is fixed. The left-hand side has a dimension that goes to infinity. So eigenvalues have to at least decay according to this bound. So the trace is bounded by the trace of the data matrix, so that eigenvalues of the Fisher of the Hessian have to decay. That they also decay exponentially. So that's what the experiment tells us. Okay. So this is one way we can understand this inequality. We can also show that the blocks of the Fisher information matrix. So these are the eigenvalues of each block of the Fisher. A block of the Fisher uses only the correlations of the gradient of the log likelihood function with respect to weights of that own layer. So you're not going across the layers to search for correlations. You're using only one layer by itself and setting all the others to zero. This is a quantity that is a little easier to analyze. We can show that every eigenvalue of this block is dominated by the eigenvalues of that particular block's outputs. So these are the activations. HK are the activations of the kth layer. And I can take the activations of the kth layer, calculate the correlations and the eigenvalues, and the eigenvalues dominate what happens to the Fisher matrix of that particular block. If you think a little bit carefully, this is not a very complicated calculation because it is just a linear map that connects the Fisher and the outputs of that block, right? Up to the nonlinearity coming there. So, but the point is that we can say something about the eigenvalues of every block. We cannot say anything yet about the eigenvalues of the entire matrix because basically, even if you assume that the weights are random, the eigenvalues of successive applications of different layers can just like, you can do anything you want to the eigenvalues. So you cannot prove that the Fisher is sloppy if the inputs are sloppy, which is what I would really like to do. The experiment tells us this, but at least in this very weak case, we can say it for every layer. Questions before we proceed? Okay, so everything that I said, it doesn't seem to be very specific to deep networks. People have noticed this in many, many, many other areas of science. I'm showing you one example. So these are what are called intracellular signaling networks. So inside cells of your body, there are different proteins that interact with each other. and then they regulate something else. So for instance, you will have, when you travel across the world, you have jet lag. Jet lag happens because so and so protein is not synthesized. Typically, the outputs of these processes are catalysts for other processes, etc. But all said and done, you can write down these systems of equations, these systems as a system of ordinary differential equations. The input of this system or this model is the rate constants of all these chemical processes and the concentration of all the proteins, just from high school first order kinetics. The output of these systems is whatever enzyme that it regulates or whatever protein it secretes. Okay, I'm allowed to think of this system as a model with an output and an input. You can calculate the Fisher information matrix of this model in the sense that how sensitive is the output to variations of the input. Okay, the eigenvalues of this Fisher are also sloppy. They also lie across huge range and essentially distributed uniformly across the system. And this is, there is a very intuitive way of understanding this. So biology, when it wants to regulate something as the output, it doesn't like to take chances. It likes to spread its input sensitivities across many, many different inputs. That way, so if one of the proteins has a different concentration today, because maybe you did not drink milk for the last 1 month, you will have certain imbalance. The output of this circuit should not change just because one of the inputs changed. Otherwise, you would not be able to function properly. So biology has evolved to be robust to individual variations of its input. It also has evolved to use only a lower dimensional function of the outputs, because that way you get to spread the effect of the output. That way many inputs take part in creating the output, and you're not reliant on any one of them to a large degree. We see the exact same thing for the networks. The output of the network comes from all parameters, all activations, and every time you can lose some, you prune the network or you set some activations to 0, stuff still keeps working. Okay. There are many other problems, very different ones, in fact. So for instance, this is the Ising model. The Ising model is a very classical thing studied in statistical physics. The probability distribution of the Ising model is sloppy with respect to the coupling constants of the Ising model. If you don't know about this, don't worry about it, but it's just a sloppy model. This is a circadian rhythm, which is what I talked about when we talked about jet lag. But there are many, many, many other models. Essentially, most places where you see data coming from some physical process, I would argue, and maybe in 10 years, I will have evidence for this also, that the model is sloppy. Okay, you can read this very beautiful paper to know more. Here is one way to use this. Okay, we'll talk about what are called pact-based generalization bounds. People in learning theory like to play the following game. They imagine that there is a probability distribution on the space of hypotheses. So little e of q is the test error of this probability distribution. You draw hypothesis randomly from q, use your test data set and evaluate the test error of this hypothesis, and little e of q is the average error of hypothesis drawn from q. E hat of q is the training error of the same distribution. So people will write inequalities of the kind test error less than training error plus some complexity term. The complexity term is simply a notion of how many different models does Q put its probability mass on. So the KL divergence of Q comma P, imagine that Q is just a Lebesgue measure. So KL of Q comma P is just the entropy, and that tells you how many different models Q puts its probability mass on. If it is a very large set, then when you fit the training data set, you find only a small set of models, and that is why your complexity term can be quite large. And one way people use these results or imagine using these results is that the number of samples that you want to use n to train your model should scale linearly with the complexity term. Okay. Now this has been done for a good 30, 35 years, maybe more. When people began to plug in numbers into this formulae, they noticed something very weird in the sense that the neural network does a very good job on the training data set. So it achieves essentially 0 error. This term is essentially 0. On the test data set, it also does pretty well. So it is, let's say, 5%, 2%, whatever. The complexity term is enormous. it scales roughly with the number of parameters. So if you have a huge network, the complexity network term is huge. So you get these absurd inequalities that say 0.05, which is the probability of you making a mistake on a new test datum, is less than 1,000. You don't need a theorem to convince me that the probability is less than 1,000, right? So when we started plugging in numbers into these kind of formulae, things don't quite make sense. Even though the formulae and the derivation, there is nothing wrong about them. If the Hessian is sloppy, then we can do just a very basic Taylor series expansion of the KL term and calculate an analytical non-vacuous bound on the generalization error. It's an analytical bound in the sense that I can write down this bound. I don't have to optimize it numerically or so. It's non-vacuous in the sense that the stuff that you get on the right-hand side is something that is less than 1. You don't usually get this. So it is not as if it is tight. For instance, for a network on MNIST, which gives the left-hand side for this particular network is about 2%. So it is 0.02. It is less than 0.38. So obviously there is big difference in the two numbers, but it is less than 1, which is reassuring. So it's not as if you need to dig around for new theory to understand deep learning. The existing theory works fine. You just have to apply it in the right way. The Hessian is sloppy if the inputs are sloppy. So the reason the networks can generalize well is presumably because the inputs have this nice structure. Okay. We have developed a bunch of numerical techniques to optimize the right-hand side. So this is an analytical bound of 0.38. If you optimize the numerical bound, and there is a tradition of doing this over the last few years, we can give essentially tight bounds for even convolutional networks and stuff, okay, without any compression, just by evaluating the bound. Here is another thumb rule to take away. So if you, two things that you can take away from this talk. One, that the data is nice. There is nothing complicated about it. And the second one is this slide. So according to the calculations, we can write down for something called as the effective degrees of freedom in a network. So I train a network with many, many weights. But as I said, not all those weights are being used, or not all the combinations of the weights are being used. We can write down an expression that says, pick a threshold epsilon, it is not that important. The number of eigenvalues that are above this threshold, roughly the elbow of this sloppy eigenspectrum, they are the real parameters that are inside your model. So this is the effective dimensionality of your trained models. It is roughly speaking the balance between you minimizing the training error, which is what these eigenvalues are used for, and you minimizing the complexity term, which is what the remainder is used for. And so when you optimize the pact-based bound, you basically pick a threshold like this. And this threshold, we simply chose to call it as the effective number of dimensions. The surprising thing is that for most networks, no matter how large they are, the effective degrees of freedom seem to be more like 0.5% of the number of weights. So if you fit a neural network with 1 million weights, you're really fitting a function with about 5,000 parameters or so. And so roughly speaking, it is not surprising that you can fit well with 50,000 samples. Okay. It is not as if the function itself is low dimensional that you're fitting. You fit a huge function, but the data doesn't let you even see all the complexity of the function class you chose. This is the only stuff that you can fit. If data is not sloppy, then you can overfit. And you will see the curves of dimensionality when you overfit. So we did an experiment where you remember the slope of the eigenspectrum like this. So we changed the slope of the eigenspectrum. On the x-axis, as you go to the right, the eigenspectrum becomes more and more flat. And on the left, as you go to the left of the x-axis, the eigenspectrum becomes more and more sloppy. So the left, this part is essentially low dimensional data sets. This part is relatively high dimensional data sets. And so we created like a teacher-student model with this, where we created a data set that that has an eigenspectrum like this by just sampling from Gaussians. And then we took a random neural network and used it to label these input images. So this is the teacher. And there is a lot of tradition of doing this kind of calculation. So this is a teacher with 100 neurons. It labels the points. And this is a student that takes those labeled points and tries to fit them. And so you can now like try a bigger teacher than a student, and a smaller teacher and a student, and lots of different combinations like this. What you notice is that irrespective of the ratio of the teacher and the student, how big or small they are, if the data is sloppy, then your test error on data created by the same teacher is small. If the data is not sloppy, then the test error is large. So you can overfit if the data is not sloppy. Doesn't mean that you have to. There may be ways you don't, but at least if you train like this, you don't you do overfit. But here you definitely don't overfit. Okay. So this is kind of the complement of the result that says if data is not sloppy, then you can overfit. The first part of the result says if data is sloppy, then you don't overfit. How much time do I have? Allow me to skip this slide. So this is roughly speaking my picture, mental picture of how training looks like in the space of functions for neural networks. And the stiff degrees of freedom, which is the large eigenvectors of the Fisher information matrix, they are the ones that are being learned predominantly. This is something that we have seen in experiments. And the tail of the eigenspectrum, you learn it either very late in the training process, or you don't learn it at all when you stop. So learning in the space of functions corresponds to you initializing at some function, a function which predicts chance accuracy on all images. And you fit these dominant degrees of freedom to some place. And let's say you end up here when you fit the function. Now, what you will also notice from many other problems that people like to train networks on one data set and then evaluate these networks on a slightly different data set, and stuff essentially works. I can take a network trained on cats and dogs and then modify it a tiny bit and make it look like, and get a network that is trained for mangoes versus strawberries. The reason this works well, presumably, and we are trying to work this out, is that different tasks, they lie very close to each other. They're only separated from each other in the sloppy dimensions, in the redundant dimensions of the eigenspectrum, and they share the essential structure of the data. What makes natural images natural is the essential structure. What makes apples apples and mangoes mangoes is the slightly inconsequential structure. So that is the structure that you modify in the network when you adapt it. And that is why it doesn't take a lot of effort to modify it. If you have to go all the way here to some other place after training, it will take a lot of epochs. Okay, so transfer learning, multitask learning, meta learning, these kind of things work because the tasks are very similar to each other. This is one kind of theory we are building using this geometry. Any questions?
Kind of going back a little bit, trying to understand the sloppiness. And it seems like, at least in the biological space, but probably also in engineering studies, there's a flip side, which is that if you are insensitive in all these directions, are you then by definition very sensitive to changes in those eigendirections?
Yes.
Right. So is that a trade-off that is being made? You can't get away from that sensitivity. Sometimes you want it. I think philosophy kind of like gives those two sides of learning. But then once you've learned this, you change, you get to the flat dog, right? And then you change to red, also
yeah, so I think that's a very interesting point. You are very sensitive to the combinations of those parameters. Now, if you think about what the parameters are in a physical process, there would be some variable that is either something that you measure or like some other a protein or like a impedance with respect to some other dynamical system, etc. So these are all bare parameters that have meaning. And you will, unless you have an adversary that comes in and affects the bare parameters in exactly the way that hits the sloppy space, you will not suffer. So I had done some experiments where I looked at adversarial samples, and they do seem to affect all the dimensions of the input vectors. There are ways to hurt a low dimensional model but you have to do a lot of work. Any other questions? Yes.
Simple question, what are some like real world examples of non-sloppy input data sets?
I like to say that I will buy you beer if you find me one. I haven't found it yet.
Thanks for that question. Could any of these findings be used to like help find like the best pre-training set?
Yes. What we have been trying to do is basically build some kind of a understanding of there are different training sets. So let us say that this is the training set you have, cats versus dogs. This is the training set you want, or this is the model you want, mangoes versus strawberries. Now you get the choice. You can either train on cats versus dogs, or you can train on ships versus boats, and many, many other such choices, right? What we are trying to understand is what makes these data sets the same or different from each other. And what we keep finding is that all data sets seem to be pretty damn close to each other. So training on these things that look like natural images is very, very similar, irrespective of which ones you choose. There are small differences between the two, but not big ones. Cool. So I want to give you a sneak preview of this other paper that we had, which asks a very weird question, in the sense that you want to train a model. Everyone wants to train a model. Everyone has some data to train this model. What is the best way to use this data? I'm not interested in finding a model. I'm trying to find ways of using the data in an optimal possible way and convince myself that this is really the best thing I could do in the sense of gleaning information from the data. Okay. The reason this is interesting is that data is a fundamentally finite quantity. In machine learning, we have never appreciated the fact that data is finite. You always see stuff where n goes to infinity. Well, that's the most boring thing. In machine learning, we should really let n go to 0. That is what learning means, right? You and I do fine with few samples, so should machines. To motivate this, I want to do a simple experiment. So let's say that I give you a biased coin, and I would like you to estimate the bias of this coin. If you want to do a Bayes law for this experiment, you will put a prior, let's say from 0 to 1, a uniform prior from 0 to 1, and then toss the coin many, many times until your posterior collapses, right? So you will need to do an infinite number of coin tosses until you get the exact bias of my coin. This is easy to see. The reason you have to do an infinite number of coin tosses is because your prior believes that there are an infinite number of models. Everything from 0 to 1 is a valid hypothesis a priori before looking at the data. And that is why you are doing all these coin tosses, to localize them, right? But if I were to change the game and ask you, if I only give you one coin toss, what prior should you pick? So think about it like this. I allow you one coin toss. You get one bit of information about this entire experiment. With this one bit, you can at most distinguish between two models, not an infinite number of models, between two models, right? So the name of the game is to find the two models that you should choose that will be nice in some sense, will be the closest to them when you look at the test data. Okay. So this is how Bayesians started thinking in the late 70s. They got very bored of using subjective priors, and they wanted to find objective priors that have some underlying objective that is being optimized. And this is a concept that is called a reference prior. So it was started by this guy called Bernardo in the late 70s. And a reference prior is a prior that lets the posterior be maximally dominated by the data, and by definition, minimally dominated by the prior. This is a very different way of thinking about priors and posteriors than what we are used to in machine learning. When you think of SVM or weight decay and stuff, someone told you that, look, data could be noisy. So that is why we should bias the hyperplane to lie near the origin. And that is why we should minimize the norm of the weights. So you don't trust the data. You believe some of it could be noisy. And that is why you use the prior to protect yourself from fitting the data too much. This is the entirely opposite way of looking at things. If you have few data, you better trust the data. I mean, you're killing a mouse to get a datum, so you might as well trust it. If you have few samples, you want to think of a prior as a way of carving out the hypothesis space to find the right set of models, not just reducing the space to prevent bad data from being explained. Okay, so mathematically, let us talk about this picture first. So in the coin tossing example, turns out for one coin toss, the reference prior will pick a prior that has half probability at 0 and half probability at 1. These are the two models that you should use before you toss your coin. And one intuitive way of understanding this is that when you toss the coin, it either comes heads or tails, right? So after the coin toss happens, the posterior corresponding to this prior has completely collapsed. It has collapsed, and it could be wrong, but it has collapsed. So you get to make a choice of which model you believe is the truth. Okay, it's a very non-intuitive concept, but it's very fundamental in this modern world where we are trying to solve problems with very small amounts of data. Mathematically, as I said, it boils down to you saying that there is a posterior W given Zn, Zn being the samples. There is the prior pi of W, which is your prior on the models. You want to, there are weird mistakes here. So you want to maximize the KL divergence between the posterior and the prior. Okay, so you want to let the data, the likelihood term dominate the posterior. And that is what this boils down to. So you can think of this as a maximization, forgive me the infer, of the mutual information between the weights and the data points. You don't need to know the samples to do this maximization. Mutual information only depends on the distribution of data. So you can optimize this given the distribution of data. And fundamentally, if you think about this, the reason there is an atom at 0 and an atom at 1 is because there is no model beyond 1, and then there is no model to the left of 0. So if you know something about what your model class looks like, what your hypothesis space looks like, then you can select from it interesting models by convincing yourself that no data will ever have a solution with a bias greater than 1. Okay. If I give you more coin tosses, then you can put mass on more models. If I give you 50 coin tosses, there are many more atoms. In general, you can prove that the reference prior is always finite. It is always, no matter the hypothesis space, it is always supported a finite number of atoms. And again, this is a very fundamental fact about data being finite and you having only finite number of options to choose from after you look at the data. As n goes to infinity, the reference prior converges in one dimension to Jeffrey's prior. In multiple dimensions, it's close to Jeffrey's prior, but doesn't really converge to it explicitly. But so things are sound for infinite data, but for finite data, they're really interesting. Okay, here is how a reference prior looks for neural networks. So we implemented this. This is probably the first time anyone has ever tried to implement this after 50 years of building it. You will only see it as like some half-page calculation in a statistics class. Probably the very first time someone tried. So you can optimize this mutual information using what is called the Blahout-Arimoto algorithm that you will see being used a lot in information theory also. And here is how it looks. So we took about 3,000 possible atoms that could be this prior. And now we are trying to find the locations of these atoms. So it's like taking my coin tossing example and then initializing 2 atoms at 2 arbitrary locations and then optimizing the mutual information to find the right locations for them. Okay. The blue points are all these initializations. And as we optimize this prior, they go to these green parts of the model. Okay. So you see that this is MNIST with 2 classes. And 3,000 networks being used. One atom is one network, because we know that the prior is always discrete, so we can always represent it as a bunch of particles. And you see that these particles, they all go far away from each other. And this is very important because these two atoms, they are maximally far away from each other, even if there are just two atoms. These atoms, they lie far away from each other in the sense of the probability distribution that they express. It is uniform on the space of distributions. And Jeffreys prior, people might know, is flat on the space of distributions, the uniform distribution on the space of models. Okay. So this is a very intuitive way of understanding what this prior does. It just takes a very large hypothesis space and then spreads out on it as much as it can to create a maximally different set of atoms. And what happens when I show you some data is that one of these particles strikes gold. One of these particles has a very high likelihood on that data, and all the other particles collapse. They have no very little likelihood. So your posterior collapses effectively. Okay. So in my mental picture, if this gray part is the space of all functions expressed by neural networks, if the data is sloppy, this space of functions is relatively low dimensional. This is what I have been trying to say, and this is what I've drawn as a thin manifold. The reference prior finds points that are the boundaries of such manifolds. They are the most diverse models that you should use with finite data. If you give me more data, then the reference prior will start putting atoms on the interior of the manifold. And at infinite data, it will treat the entire manifold as a legitimate set for space of models to fit. Okay, but simple models lie on the boundaries. The reference prior finds the most diverse set of simple models. This is, I think I don't have time to talk about this, but it's a very clean formulation for semi-supervised learning. You can use the unlabeled data to get the distribution of the data and now optimize the mutual information with respect to the distribution of data by treating the unlabeled data as your samples. Okay, so when you write it down, it is very interesting in the sense that a lot of current algorithms for semi-supervised learning and self-supervised learning, they implement this objective in bits and parts. So with this one objective, you can just start deriving them in a big list, one by one. None of them implements the entire objective because they usually come at this from a more ad hoc, intuitive sense. But together, the union of techniques that they have discovered is equal to this objective, to all the stuff that is inside this objective. If you implement this objective, it also works quite well. So for instance, this is 85% accuracy on CIFAR with 5 labeled samples from each class. And then all the other samples of CIFAR 10 are being used as the unlabeled samples to fit your reference prior. Okay, so this is not so much an algorithm for doing semi-supervised learning. It is more of a theoretical way of looking at semi-supervised learning. They typically like to fit one particle, but as we saw, fitting many particles and letting the posterior collapse to one of them is the sound way of doing things. If you pick one particle, then obviously you can be wrong in where the task lies. I'll stop here. So the key takeaway from this talk is there's many surprises in deep learning. I'm pretty sure there are more to come. But I believe, and I'm trying to convince myself that these surprises are a function of the input. They are due to the data set. They're not so much due to the architecture, the way we train, what regularizer we use, etc., because they all seem to work equally well. It is a little surprising how strong the structure in data is. And what I'm trying to do is argue that typical learning problems, classifying cats and dogs, like saying that this chair is a chair because it has corners and a seat and 4 legs, etc. These are problems that we created upon this world. And so they are simple in some sense. We do not create complicated things. It's not as if I'm asking you to classify the number of little squares on the carpet here. I'm asking you to classify whether this table is flat. There is not that many features you need to say that. Okay. So typical learning problems that we create are somehow simple. And so the artificial networks basically just latch on to this structure. And now it is a very interesting question of science as to what causes the semantics that we impose upon these physical observations of the world to be simple. So I'll stop here. Thank you. Yes.
Kick the can a little bit down. We'll find those points within this optimization, but then of course you have to choose a fire to get your initial particles if you didn't optimize, right? So how, you know what I mean, in the this picture there where you went from the blue to the green, like you had to pick all the blue points and you picked them there.
Doesn't matter so much where you pick them, because they'll all, like, you pick them in whichever way you can. In this case, the networks were just initialized randomly, so they all predict chance accuracy on the classes. So they seem to lie close together in this low dimensional projection of this function space, but they can be anywhere else and they will flow to the right locations. The solution is the green points. And yes, it is also convex in pi. Yes. Yeah. Any other questions?
Yeah, the first part, if we could express deeply the data in the eigenvector space, like the training will be block coefficient training of the.
Yes.
Probably them for any big data set.
Yeah, so you expect that if you project the data in this space, then you only have to fit these functions. But what is true is that this will give you 95% of the accuracy. But if you want the remaining 5, you have to dig through the entire tail. So you can be happy with 95. And 10 years ago, we were happy with 95. Now we want more. So you have to keep digging the tail. So this is not saying that the data is low dimensional. Data is full dimensional. It is just that the sensitivities are nice, created by nature for you. And a lot of, for simple problems like classification stuff, this is why you get hurt by projecting the data.